Hi, it's time for me to finally fix the issues with my custom EEPROM replacement and deal with some backbleeding of the battery power onto the circuit. Let's get into that.
Hi, my name is Adam. I'm building a 16-bit computer from scratch. I hope you'll join me on this journey.
Back in video 57, I put together this SRAM on a socket with a battery and a couple of diodes to keep the battery from bleeding back out onto the rest of the build, and then a 47 microfarad capacitor to power it long enough for the battery to take over. There was yet another diode in there which was to keep the circuit power from trying to charge the battery, limit the exposure of voltage onto the battery there. It worked in the circuit. However, the battery discharged very quickly. Not quite so bad when it was out of circuit, but in circuit there was a lot of things that tried to drain the battery, and it disappeared very quickly. And so this was really the circuit that I implemented, and well, that didn't work. What I'd like to do is I'd like to explore why it failed and try to explain, because if I can explain it, that means I understand it. Well, let me restate that. If I can explain it accurately, it means I understand it. But it's my check and balance to make sure that I do understand what it is that's gone on here. And so originally in 57, I started with a Schottky diode, thinking that the forward voltage here was going to be better. And, well, so let me apply power to this. So this is hooked up to my normal 5-volt power supply. And I've got 5 volts coming over here to the diode. It's reverse bias, so it should not be putting any electricity through onto the opposite pin. And that's my understanding of how that should have worked, or how I wanted it to work. So as I measure this, and I'm going to measure it in terms of voltage, if I put one lead on the anode and the other lead on ground, I'm getting 1.8 volts of leakage. Now this is reverse bias. So if I was to spin this around so that it would conduct, 2 volts isn't enough, I'm getting the full 5 volts. Well, obviously the Schottky diode was not a good choice for that circuit. It's an easy enough test to do, and I should have done it before I even committed it to the circuit. Almost 2 volts there. Well, this was a small signal diode, which is the one that I threw out in favor of the Schottky, but ended up replacing the Schottky with one of these. Checking, make sure I'm putting this in right. So again, I've got the cathode up here at the top, the anode down here at the bottom, and that's bleeding 0.2 volts. Well, we can go into the millivolt range. 73, 74, coming up to 75 millivolts, 76. So it's slowly increasing. You know, maybe it's stabilizing at about 74, 75 millivolts. That's still more than I wanted. Okay, well, the next thing to try was this BC547B, which is a small signal NPN transistor. And the way I would have hooked that up, it would have been like this, such that the collector went up to 5 volts. This would have been my load. And then this would have also gone to 5 volts through a rather large resistor. And then my battery, well, that's multiple cells, but my battery would have been hooked up there in such a way that it had a diode there. That would have allowed some voltage to bleed back towards the battery through the diode, but it should not have been enough to create a problem for the battery, because the voltage here from the leaky diode would have been less than what the positive of the battery was. So let's test this. And to do that, what I'm going to do is I'm going to put the NPN transistor here where the emitter is associated with what the battery would have provided, and the collector is left, I'm sorry, the base is left floating. And then let's measure this pin. So the base would not have had anything on it, because there would have been no power coming from the power supply. I have to measure two of these. I have to measure both the collector up here because it would have been tied to the power rail, and the base because it also would have been tied to the power rail. And I'm still getting some bleed back on the collector and some bleed back on the base. Obviously this would be going to be 5 volts. So 3 millivolts, about 3 millivolts. That's not a lot, but it would have been enough to still create problems for me discharging that battery. Okay, I'm going to try this test again because I realized it was not architected correctly. So in my circuit, when power is missing, there is some other circuit load which ties the 5-volt rail to ground. Now this is my CMOS load, but in this circuit what I really need to do is I need to take the collector and base, those two are tied together. Then I'm going to take I'm just going to use a 1000 ohm resistor just to do this. And then another hookup wire here to go from there to ground. Let me try that measurement this time. And so over here, this is on the collector to, I can measure there because that's ground. There's no voltage. 0.4, well, it's bouncing around a little bit, but it's coming up on close to 1 millivolt. Now if I measure this side, it should be exactly the same. And it's not. And that's because I have them. No, those are correct. Those are correct. It's tough to see the wires on the blue board. That's fascinating. Yeah, I'm floored at this, that I'm actually getting no voltage, no current passing through there. So this then changes my plan a little bit. This isn't certainly what I had intended to do this video, but I'm going to take one of these NPN transistors and drop it into the existing circuit and replace the 2 diodes here, because I've got one which goes from power input off to this extra rail and then back over to the power that is going to this particular pin. So I need to add a resistor in here and figure out exactly how I'm going to pull all this together. I think I've got an extra rail. I do. You know what? I'm going to warm up the soldering iron and put this into the circuit, and this will be test number 1. I'm going to have 2 tests here that I've got to complete. Once again, the way I envision this video to start or to go derails part way through it. So, well, let's go have some fun. Okay, the first order of business is going to be to remove the components I don't need. And that's going to be this diode here and this other diode down. Wow, okay. That's going to be this diode here and this other diode down here that's very difficult to see. And yeah, this ought to be fun. Okay, let's start with the transistor. And if I orient this the same way that the illustration is, pin 1 here is the collector. So this is pin 1. Pin 2 is the base, pin 2. And pin 3 is the emitter. Collector, base, emitter, collector and base both need to be up to 5 volts, the base through a resistor. Now, that said, this is my 5-volt input right here. So my collector needs to go onto that pin, but my base and emitter need to go over one extra spot. I think I've got, okay, I've got, not sure if you can see it, but the reason it's not going in is because I've got solder right there that's blocking the path. So let me see if I can pull some of that out. All right, there it is. Hopefully I can zoom in here. This is my pin that drops into the breadboard for power. It is separated here from the pin that provides power to the IC. Pin that provides that power to the IC comes across here. So this is truly my 5-volt pin here. My base is on this rail here, which has nothing on it anymore. And my emitter is on this brand new rail that hasn't been used. So let me get that soldered down, and I'm going to use a little bit of tape here to hold that in place while I do it. Okay, the next task is to hook up the base and collector with a 10,000 ohm resistor, and I've managed to make a mess of this. I think I can do it there. Okay, let's see what I can do with that. Okay, the last task here, and I've grabbed a piece of wire and bent it up here, but the last task here is going to be to take this emitter and connect it off to my IC for power. And now I just want to beep out each of these and make sure I didn't cross anything over. And those should be connected. Okay, as challenging as that was, that might actually work. We'll have to see. Okay, I decided to do one final test with the multimeter to make sure I didn't bridge anything, and I bridged something. Can you see it? If I touch that trace and that trace, it's bridged right through there. There's a bridge right there. So, yeah, I made a mess of it. So, I'm going to try with just the soldering iron to see if I can relieve that. And if not, I'm going to have to get some more solder wick out and work on it that way. Oh, it's going to be a mess. All right, let's see if I have that cleared up here. Okay, that is as it should be. Now, do I need to add solder back? I do. I see a pin that is exposed here, so let's see what I need to do for that. There it is. Test it one more time. That's what I'm looking for. Before I get into this segment, I had to do some sprinkler work, and so I've got PVC primer all over my fingers. It's not like I took a hammer to my fingers to try to make them black and blue. That's strictly the purple PVC primer. So with that change done, if I measure the voltage here on the pins, power and ground, I've got 3.13 volts, basically 3.1 volts. That's quote-unquote keeping the SRAM alive here. But more importantly here, I want to look at what's going on down here on these pins that would be trying to drive the rest of the circuit. 0.22 volts. Let me go down a notch in the scale. And amazingly enough, I end up with a far different reading. So I can go down into the millivolt range, and I'm getting more than 200 millivolts. And why is that showing up as 1.7 volts? So here's the problem. I don't know if my multimeter is an issue or if this is an issue now. And I'm starting to suspect the multimeter. And so now I'm down to 0.005 volts. So basically 3 to 5 millivolts. And now I'm showing 3.5 millivolts. Again, I'm starting to suspect the multimeter here. That's still not zero. And so what I really want is I really want nothing to bleed back and try to power the circuit. Now, I've not put this in a circuit yet to see what shows up on the circuit as if it's trying to power it. But even that little bit of a draw could potentially drain the battery much faster. Okay, let's get back to the original plan B here. And this is what I wanted to try to accomplish in this video. I have here a double pole, double throw relay. It is one of these AZ822 sub-miniature dip relays. It is operated on a 5 volt, where is it? 5 volt coil. Coil voltage is 5 volts, and it must operate at 3.5 volts. So even at a lower voltage, I'm going to be able to get that to switch. And here's the wiring diagram that's associated with this particular relay. So if I draw my 5 volt rail up here and my ground down here, if I drop in my relay points here, then my common points, drawing not to scale. Okay, so this would be my normally closed point, and then this is my normally open point, and this is packaged in a relay. If I then add my battery right next to that, and a capacitor right next to that, and my SRAM right next to that, I've got a chip enable pin that I'm going to want to use a 100k ohm resistor to pull high when I'm on battery power. So this battery then would be connected here to pull that high. Ground I want connected to my common pin here. And my 5 volts I want connected to my pin here. My normally closed is going to be connected to the battery. So this comes up and over to there. This comes down and over to here. My normally open, I want connected to 5 volts and the power rail. So far, so good with that. The capacitor, I want itself to be connected to the IC so that it can, thinking this through, so it can drive the IC when, basically when the relay is switching back and forth. And I actually want to connect this here onto the common pin because it's basically going to be a pull-up resistor based on how that is wired. Basically based on what's powering it. So let me clean this up. So that's good. Now I have it on really good authority, and I'll stick Dave's video up in the corner, that I need to have a diode here. It doesn't need to be anything special, but I need to prepare for what's called EMF feedback. I believe that's what it's called. And allow some place for this outrush of current when the magnetic field collapses around this coil, so that it doesn't go and hurt everything else in my circuit. If I'm going to have several of these actually in my circuit, that could add up to be something that's dangerous. So I want to make sure that I'm doing my due diligence there. So that's my new plan B. And to do that, I have this little daughter strip board that I've managed to cut, and I'm going to drop my relay in here, and I've got some angle pins that I'm going to use to connect this off to the PCB here. Now, why did I not just extend it out this way like this? Well, the reason I didn't want to do that is because it actually is wide enough that if I compare it to a breadboard, it's going to be tight to fit, because I actually have to fit it between this point and this point, because this power rail is this power rail effectively on the next board. So if you look at it, it just hangs over. So I am basically a hair longer than I need to be. So I need to create some horizontal or lateral room. So I figured I'd go ahead and tilt this up like this. Now I also need to cut traces here. In particular, when I put my cradle in here, I'm going to need to cut my ground pin here. So my ground line here, so that these two are separate from the rest of this. I'm going to need to cut up here so that I can deal with power and the light coming back here. Let me get going on that, and I'll have a little bit of a fast forward for you while I pull that together. Okay, for cutting the strip board where I didn't have the luxury of taking a hole out of service, I tried using an X-Acto knife, and that didn't work out well at all. I did not feel like I could actually get through the copper. Ultimately, I switched to a thin blade screwdriver and used that to scratch the copper off, and that looked like it worked so much easier, it felt like it worked so much easier, and I could visibly get a separation between the two different pieces of copper. Before I got into cutting the daughter board, I took a moment to make sure that I understood exactly what signals were going to go onto what strip. And for the other holes, I used a drill bit like I have in the past. It works well. All right, let's put this thing together. As I put this together, keep an eye out for a couple of mistakes that I make while I'm doing this. I ended up putting a few things out of sequence here. One mistake I made was I put the pull-up resistor where the pins were going to go for connecting into the breadboard. So I ended up having to pull that out and find a different spot to put that. Second mistake I made is I neglected to connect the ground wire for pin 14. And so I ended up having to fish that under the cradle after it had been completely soldered down. And finally, the battery holder, I ended up putting one row of pins too close to the relay and ended up having to move the battery holder down one row so that I could get the relay in. Nothing really the end of the world, but certainly things that should have been planned better for. Okay, now let's talk about these pins a little bit. Now I realize that I'm trying to solder the pins to the strip board on the same side as the copper and trying to get a good electrical connection where an electrical connection was not intended. I end up struggling with that. And it ends up being a very difficult process for me to get those pins actually making a good electrical connection to the strips of copper. So I need to come up with a better way of doing that, and I'm not exactly sure what that is going to be yet, but I am going to have to find something. That was, well, an ordeal. I certainly soldered some things out of sequence, which made that far more difficult than it needed to be. I believe I've got all of my connections correct, but I'm going to tone it all out and double check and make sure that things are actually doing what they should be doing. So let me go through that exercise real quick and we'll see how things go. Now, as I'm going through and trying to test out each of these electrical connections and fixing the ones that I find that are incorrect, I realize now that I'm probably better off coming up with some kind of a solderable protoboard. Very similar to a breadboard would probably be good. Now, I know I can purchase these, but I think I can actually make something that suits my needs very specifically. And then I have something that's purpose-built just for my needs. And then I have an easier time prototyping my circuits on something that looks like a breadboard. Okay, now let's do some testing on a breadboard. Okay, let's start by seeing if I can get this relay to trip properly here. And that, I don't know if you can hear it, it is bouncing all over everything, which is not the way that's supposed to happen. The first order of business is to test to make sure that I understand exactly how the relay is going to work and what behavior I can expect out of it. I should have started with testing on a breadboard, but I figured I could go straight to the proto board, and I think I pay for that mistake. That's working exactly the way it's supposed to. So I have something wired up grossly incorrectly here. That has connectivity when it's not supposed to. That is a problem. All right, well, let's try that again and see if I can't get this to work properly this time. I spend at least the next 20 minutes or so looking at the coil and making sure that it is wired up properly. I even go so far as to pull out the breadboard again and wire up a good working test with an LED load so that I can test that things are actually going to work the way I expect them to. Okay, I've run into some problems. First of which is I lost some video, and that was related to troubleshooting the lines here associated with the circuit board and what exactly went into the relay. This is what my original solder up plan was, and this up here is what I've got now. The lines marked in green are the ones that were correct. The ones marked in red here are the ones that were not correct. And ultimately what it boils down to is if I take these and superimpose it over the diagram here, ground would get connected to the negative battery. Well, that ain't right. And VCC would be connected to the positive battery. Well, that ain't right. Ultimately, I had to make sure that each pair was a complete voltage source, both positive and negative, VCC, ground, what have you, from the 5-volt rail or from the battery itself. So having got that fixed, I now have the relay working, and I believe I caught the relay failure on video. But the relay itself is now switching properly back and forth between power. I also discovered a number of pins that still were not connecting properly, and I did have to go back through and resolder those yet again. But now I'm having an issue with getting the SRAM to program. If I drop the SRAM into the socket here directly, it will program. But if I leave it in this circuit, then it will not program properly. Now, to troubleshoot this, I've gone through and I've beeped out every single pin to be connected. I have checked to make sure that there are no crossovers multiple times. And so the only thing that I can think of is this pull-up resistor right here, which is a 100K ohm resistor. But if I pull this one, this is a 10K ohm resistor. And I went with a higher value resistor to try to reduce the amount of voltage that was flowing. Basically try to limit my current a little bit. That may or may not be causing me problems. I'm going to have to, let me demonstrate the problem for you first. Okay, so if I get into Minicom, there is on the bottom down here, there is a test where it will actually try to program 32 bytes and then turn around and read 32 bytes. So I'm going to try to do that at address 0. And it is not able to do that read. So it thinks it wrote it, but it did not actually read that byte back off of the EEPROM. I've probed a lot with the multimeter, and I am not able to determine what's going on. So now it's time to break out the oscilloscope and see if I can figure out what's going on in reference to these signals. Let me get the scope out. With the oscilloscope, I start off by probing the chip enable pin. That ends up proving nothing on its own, so I end up hooking in the address bit 1 as well so that I can compare them in conjunction with each other. That gets me nowhere other than an observation that the voltage appears to be somewhat low. And so I go to the data sheet and check that out. I'm chasing ghosts at that point. Okay, I'm actually hooked up back here onto the right enable pin, so let's redo that test. That's not working the way I want it to. Right enable is low. Is it genuinely low? Yeah, 0.5 millivolt. I believe that's my ground. There's my VCC, there's my ground. Red and black, there's my common ground. Yeah, that's pulled low. Right enable is good. Okay, I'm going to try that test again, this time with the address line. So triggering on channel 1 when it goes high. So on my right enable pin, I believe to be genuinely low. Yep, that's what it looks like. So the next one might be the output enable line. Okay, I spend a few minutes doing some digging around with the oscilloscope on the output enable pin here before I decide to break out the Tommy Prom code and actually look to see what's going on. Alright, so down here I've got this read byte function which disables the output, disables write, enables the chip, enables the output, reads the data bus, and then disables output. So I'm interested in this enable output function. This is a very simple function which basically does a digital write of the output enable pin to low. The output enable pin is A2. So let's see if we can test that and see if A2 is ever actually making it low. Okay, I've got my oscilloscope hooked up here, and I'm looking at the A2 line, which should go low at some point, and it does not. As I'm going through and testing this, let me zoom out here, 100 microseconds per division, 1 millisecond per division. There's nothing that's actually triggering that at all. So, unfortunately, I think I have damaged the Arduino that's on here, and I need to replace that. That ought to be fun to do. Real quick, before I go down that path, I've put the other board in here. This is the one that has the transistor on it. And therefore, if I try zapping, that works. And there's the test pattern. So how is it that that works, but the other one does not? Okay, I'm going to try popping, eliminate as many variables as I can. Let's put this in directly. Okay, that's directly in the IC, so let's see what happens when I try to program that. That works. And yes, there's that test pattern. Okay, so there is something with that board, and I am not sure what it is at this point. Okay, I'm guessing at this point I've taken the battery out here and I rebent the pins to make sure that they were straight. Let me give this a shot and see how this works. Still does not work. Okay, now I've removed the relay, taken the whole thing off just to see if that was creating problems, and let's try the test again. Yep, still something wrong. There's something with this board that I just cannot get to the bottom of, and I do not know what it is. Once again, if I put the SRAM in directly, so there's no cradle or anything, it works just fine. So I have done something totally wrong here. Okay, I've been quite myopic in trying to troubleshoot this thing, and I have been convinced that there is some connection side by side which is shorted, not thinking to measure VCC to each connection and ground to each connection. Now, with ground, when I get up here, it's not shorted to VCC. Well, that's a pretty darn good thing. But the right enable pin, that's a dead short. So it's always going to be low, no matter what the Arduino in the Tommy Prom puts out on that pin. Well, let's go take a look at the data sheet again for the memory. Okay, so during a read cycle, chip enable is going to be low to enable the chip. Output enable is going to be low because we're trying to read. Both of those are by design. But write enable is also going to be low, and that's artificially pulled low because of the short. So if all three are low, then it's still in write mode, which means that when you're trying to read, it still thinks it's trying to write. Okay, well that makes some sense. Now what do I do to clean that up? So the top two pins here, or top two holes, 4 pins, are supposed to be cut and separated from these three. So this pin here, which goes into the Arduino, this which is, well, it sits underneath the cradle here, and then this pin, which is the cradle. There's supposed to be a separation there such that this doesn't connect to that. If I look at the wires I've got connecting everything up, this pin is coming off ground from the Arduino or from the breadboard. That comes over here to this far row, which comes up from there to the upper part. So that would be this section of those two pins, which has a jumper here that goes over to this common ground. And then tucked in here is a connection which brings it over to the ground for the socket. So I look at this and the problem has to be somewhere in this cut. It is not properly separated. What I think I'm going to try to do is just see if I can grind that out a little bit with a screwdriver. Let's see. And I don't know if that's going to do it or not. Okay, that's actually looking like I might actually have it. So if I put the chip in, I should be able to do a test program of this. Still incorrect. But notice the address is different. But now I've got to figure out what's going on with that. So dumping the data here, let's see here, I believe it's all 16 bytes there. If I look at the input versus the output, so this is what the results were. I've got A in address 0, C in address 1, C in address 2, binary 000110. It's almost like the address isn't picking up the least significant bit. Alternatively, if I look at all of these values, every one of them is odd. Every one of them is odd. So it's almost like the least significant bit is always being read or written as a 1. So now the question is the problem on reading or is the problem on writing? So hex 41, hex 42, hex 43, 1 would be 3, 5, 9, 1, 1, 1, 3, 5, 9, 1, 1. So I'm either programming every bit as programming every byte as the least significant bit high, or I'm reading every byte as the least significant bit high. And then go back to the overhead here, because I still do have my test points soldered in. So this is bit 2, bit 1, bit 0. This would be address 0. So I should be able to at least look at address 0 very easily on the scope and determine if that's actually being toggled or not. I'm gonna have a little bit harder time with the address, or I'm sorry, the data line 0. Okay, let's define the problem here. If I go to try to test, write failed. How can the write fail? Do I not have it in right? Okay, if I attempt a test, it fails at the first address. And if I dump the contents of the EEPROM, these first should be A, B, C, D, E, F, G, H, I. And every even address contains an incorrect value. So now if I pop this out and remove the SRAM from the cradle and drop it in the programmer directly and redo the test, it's actually successful. And if I look at the memory, you can see that it actually contains all the correct values that I was expecting. All right, so I still have a problem with the cradle. And since it's every even address always contains an odd value, it's either the least significant bit of the address, which has conductivity, or the least significant bit of the data byte, which has no connectivity. So I've got some soldering to do. While I'm at it, let's just test each one of these. Let's try that again. Oh, now that makes me happy. Okay, next challenge is to remove all these little pins that I put in place in order to do the debugging. Okay, let's do just another test and make sure that still works. I haven't heard anything. Good. Next step here are these two that need to come off. Let's test this again, see what happens. That looks good. I'm having trouble inserting it, but that does actually look pretty darn good. So now if I take it out, my relay should kick in, should have switched over, and this should be now holding the data to the point where I can drop it back in here. And then if I switch back and dump again, I lost it. Let's zap it again. Write failed. Why am I having problems with writing? There is something going on with getting this seated right. Okay, we've got to test it again to make sure that we can write on the SRAM directly. Okay, I can write on it directly, so something is still not right with this thing. Let's take a look here. I finally got it working, and it actually holds all the correct data. So what did I do to get it working? Well, I took that flat blade screwdriver and I went down between these two traces here and made sure that I had clean separation. I thought there might have been just a hair, just a smidge hair of an overlap. So got that cleaned up and it now programs. And if I remove it, I can feel and hear the relay disengaging. And if I put it back in, I can go back over and dump the EEPROM and it still holds the data. Well, so what's next? Well, I'm going to take both of these and put them in the circuit and let them sit for a little bit and determine which one of them has the better results on the other end. Okay, well, I already recorded my wrap up and went to program this and put it in circuit, and it is failing again. And so unfortunately, if I'm going to produce something, I need to call this at this point. I'm gonna call this a fail associated with the relay. I'm gonna put the one with the BJT transistor in it into the circuit and see how the battery lasts. I'm heading off for vacation for a couple weeks, and it'll take me a week at least once I get back in order to produce another video and get that released. So you're probably not going to hear from me for a few weeks. Unfortunately, this particular one with the relay, I'm going to have to call it a fail. It's just not working. It's been far too fussy. It's been far too difficult to debug. That's not to say that I'm not going to pick it up and try to sort it out once I get back from vacation, but I'm done with it at the moment. Next up, I have some power issues to look at on the backplane, and the register backplane, and I want to take a look at those and see if I can get those sorted. I need something different other than this to stare at for a little bit. But on the other hand, I do prefer this. It's much simpler and a much cleaner design. So if I can get good enough performance out of this, sometimes good enough is just exactly that, good enough. So if that's the case, then I will very quickly turn this into a breadboard that I can turn around and populate and start making use of it. We'll see you soon.